What is big O notation? Why is it important? What does it measure? We have common big O complexities, O of 1 and O of whatever. What are they? I'm going to explain big O notation and its types using Owanbe Nigerian party scenarios. So you're definitely going to understand it. First things first, what is big O notation? Big O notation is how we measure how fast or slow an algorithm runs as the amount of work that it does, the input size, increases. That's a common definition. It's a mathematical way of describing how an algorithm performance scales. And trust me, I think it's very important for a software engineer to know big O notation. There are some companies you'll not get into if you don't even know it too. But back to work. Why is big O important apart from getting jobs and all? Why exactly is it important? Number one, it helps to predict performance. Big O helps to determine how an algorithm will behave as input grows. Number two, it helps to compare algorithms. You're able to choose the best approach for large scale application. And number three, it helps to optimize code. With big O, you can avoid slow algorithms that become inefficient as data grows. So big O measures two major things, yeah? Time complexity, space complexity. Time complexity is how fast an algorithm takes to run as input size grows, while space complexity is how much memory an algorithm needs as input size grows. So, big O notation focuses on measuring these two things, the time and the memory usage. But in this tutorial, we'll majorly be focusing on time complexity. So let's move into analyzing our big O complexities with Owanbe scenarios. Number one, O of 1. O of 1 is called constant time. But in our Owanbe explanation, we will call it the VIP entry scenario. So think about it. You are a VIP guest in a Nigerian party. Of course, if you're a VIP, you get special treatment, right? You get your food served immediately you get to the party. Nobody's delaying you. They want to treat you specially because you're VIP, right? So no matter what time you get to the party, you get served. No matter the amount of guests at the parties, you get served immediately. So whether there are 10 guests or 100 guests or 1,000 guests standing outside, you are VIP, right? You go in and you get served immediately. The time it takes you to get served as a VIP guest never changes. So let's move into technical time. This algorithm, O of 1, it runs in constant time because it does not depend on the input size. Like we said, even if there are 1 million guests at the party, because you're a VIP guest, you get served. So regardless of the input size, the algorithm maintains constant time. No matter how many elements exist, the algorithm executes in the same number of steps. 10 elements, 100 elements, 10 million elements, the algorithm still takes the same amount of time. That's number one. O of 1, constant time, VIP entry. Don't forget, super fast. It is the best case scenario in computing. It is super fast. It's like a perfect world. Don't forget, O of 1, constant time, VIP entry. Now let's move to the next one. O of n is linear time. Think of O of n as a finding your friend in the crowd scenario. So you're at a Nigerian party and you need to find your friend. Yeah? You're searching for your friend. So you're searching one person after the other. You're looking. Is this my friend? No. Is this my friend? No. If there are 10 guests at the party, you probably would have to check 10 times. If there are 100 guests, you're checking 100 times. So in this case scenario, O of n, the more guests, the more searching time. So the algorithm loops through each item once. So meaning that the time it takes increases linearly with the number of items. So execution time grows directly with the input size. And the worst case scenario in this case is if your friend is the last person you check. So that's the worst case scenario. Say you have 100 guests and then you check and your is the 100th person. But at the same time, your friend can be the second person or the third person. But regardless of the case scenario, the execution time increases directly with the size. And the performance, this complexity is okay for small inputs. But as data grows, it becomes smaller. But for small inputs, bravo, it passes. So, number 2 down, O of n, linear time. Finding your friend in a Nigerian party. Now let's move on to the third one. O of n raised to power 2, quadratic time. Think of this as a matching scenario. If you're Nigerian, or if you know a Nigerian, if you go to a Nigerian party, people are usually wearing the same clothes everywhere. So you see groups of people wearing the same clothes. Some people might be wearing Ankara, some people might be wearing lace, some people might be wearing whatever. You know, they match Ashwebi, right? We call it Ashwebi. So suppose there is a fashion contest and you need to check which guest wore matching Ashwebi fabrics. So you pick one guest and you compare them with every other guest to see, okay, are you matching with anybody? So for each guest, you compare their fabric or their outfit with every other guest. Now, if there are 100 guests, you take each guest and compare their fabric with every other guest. So you're literally doing a 100 times 100 operation. So you are going to be doing a total of about 10,000 comparisons if there are 100 guests. So, as you can all see, the more the guests, the slower the guests. Technically, this is common when there are nested loops. You put it in a loop. JavaScript developer, put it in a loop. They will soon arrest you. But yeah, I'm just joking. But yeah, it is common when there are loops and loops. So the time grows exponentially as the inputs increase. Remember, with O of n, the logarithm time, the time goes linearly. But in this case, the time grows exponentially. So if you have n number of elements, you are doing n times n number of operations. Remember, we have 100 guests, we are doing 10,000 comparisons. So if you have in a loop, congratulations. O of n raised to power 2. Your algorithm is increasing time exponentially. Performance, it is very slow when you are using it with large data inputs. And if possible, avoid it. Thanks. Next on the list is O of logarithm time. Think of it as finding jollof rice before it finishes. If you're Nigerian, you know that this is a battle. Jollof rice will always finish, right? But jollof rice does not exactly finish because there are people that abort jollof rice. So it doesn't exactly finish. If you know your way around, if you know how to search, you can find that jollof rice. So maybe there are people or servers or Nigerian aunties hiding jollof rice in different sections of the oil. And you're trying to find the jollof rice, right? So instead of checking each table, you divide the oil into sections. So you search this row, you divide it into section and you're searching section by section. So you check the middle of the oil, the jollof is not there. You go to the left or the right, the jollof is not there. You're searching, you're dividing your search. In this case, the more the guess, the fewer the steps. So if you have a very large oil, you're able to see through and divide properly. Technically, this happens when an algorithm cuts the search space in half each time, like binary search. So instead of checking each item one by one, the algorithm is doing some form of divide and conquer. So that makes it really fast. Another example to explain this, if the divide and conquer, finding jollof in a all doesn't, is if you're looking for your friend's name in a phone book. You can search one by one from the beginning, or you can open it into half. If the phone book is sorted alphabetically, you can go to the nearest alphabet. You can, divide it, open it to the middle, check if your friend's name is before or after. If your friend's name starts with letter O or letter G and you open to the middle and it's letter O, that you're going forward, you're not going backward because G is before O. So you're dividing. That makes your search faster as opposed to checking one by one. That's exactly how O of log n works. You have an element in an array sorted. So you start with the first element, you move to the middle number, to the middle element. If the middle element is the one you're looking for, congratulations, your searching is over. If the middle element is smaller than the target, then you know that your target is on the right side. And if the middle element is larger than your target, then you know that your target is on the left side. And you repeat the process with the remaining half until you find your target. Divide and conquer. In this case, look at this function, find jollof rice function. You have the array, which is the tables, and you have the jollof table, the table you are looking for exactly. So we have a while loop, you're dividing your congruent until you find, and that way you're able to save time. So O of log n is really efficient when you have large data and you need to find something ASAP. Next up is O of n factorial. It is called the factorial time. Now think of this as planning sitting arrangement. This would not happen in the Nigerian wedding on a normal day, but let's pretend that in Nigerian parties, they plan sitting arrangements. So you are planning a party and you need to figure the number of possible sitting arrangements that you will have for a group of guests. If you have 3 guests, then there are 6 possible ways to arrange them. Yes, 6 possible ways. If you have 4 guests, then there are 24 possible arrangements you can have. That's 4 factorial is 24. 3 factorial is 6. 4 factorial is 24. So there are 24 possible ways you can arrange it. As you can see, the time it takes increases very quickly. For 3 guests, we have 6 arrangements. For 4 guests, we have 24 arrangements. In this case, your algorithm is trying to generate the total number of permutations possible. And your time complexity can go really fast. For example, if you have 6 inputs, if your n is equal to 6, you're going to have 720 operations. 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. 720. Now, if you have 10 inputs, guys, guess crazy. With 10 inputs, you would have 3,628,800 operations. With O of n factorial, it's almost as if for every item you are adding another extra loop. That's how it works. So the performance can be very slow with large inputs due to factorial growth. Next up, we have the O of 2 raised to power n. This is the exponential time. O of 2 raised to power n. Now, maybe you're at the party and you want your guests to come and snap pictures. And you're trying to combine guests together for arrangement for the picture. If there are 3 guests, you probably have 2 raised to power 3, 8 different combinations of guests that you can bring together. If you have 4 guests, you probably have 16 combinations. So the execution time doubles with each additional input. This complexity is common with problems that have subsets. And they are also very slow and inefficient for large data inputs. For example, if you have an input size of 5, the algorithm is performing 32 operations. That's 2 raised to power 5 is 32. If your input size grows to 10, your algorithm will be performing 1,024 operations, 2 raised to power 10. So it's not exactly that efficient. It slows down significantly with larger data due to the exponential increase. Last but not the least, we have O of n log n. I know we have O of n, we have O of log n, and now we have O of n log n. To be fair, it's like a combination of the 2 complexities. O of n plus O of log n equals to O of n log n. But it also has its own explanation. It's not that straightforward like that. So it's like you're sorting guests by their names in an alphabetical order. It's giving O of log n, but now in this case, you sort and you merge. So it's you split the list in half, sort each half separately, and then merge together again. So O of n log n is a log linear time complexity. Log linear time complexity. It performs better than O of n raised to power 2, which is exponential, but it's still slower than O of n. It is reasonably efficient for large data inputs. And that's about it. Let's go over it very quickly. O of 1, remember, constant time, VIP entry. It's super fast. The algorithm runs in constant time no matter the input size. We have O of n, which is the linear time. Look at the example, finding your friend in the crowd. Do you remember? Time increases linearly and it is okay for small inputs. Then O of n raised to power 2, which is the quadratic time. In this case, you are checking matching assure, and the time scales exponentially. And it is slow for data inputs. And we have O of log n, finding jollof rice in Eden area by dividing the search area. Remember, so the time increases logarithmically as the search space is divided. And it is efficient for large inputs. We have O of n factorial. That one is terrible. Planning every possible seat arrangement. It is very slow. We have O of 2 raised to power n, the exponential time, checking all subset of guests. The time doubles with each additional element, so it slows down really drastically. And then we have O of n log n, which is the log linear time. It's efficient for large inputs as well. So with this viewpoint of mine, I hope I've been able to convince and not confuse. Just joking. I hope you get a gist of what big O is, why it is important, and all of the common complexities that we have. If you enjoyed this video, like, don't forget to subscribe, don't forget to turn on your notification for more tech and coding content. See you in my next video.